It's just right, okay. I want to do a quick overview of an update for the site update for Indiana University. I run the Science Community Tools Directorate, which is more or less responsible for a lot of different end-user support tasks, both for our HPC systems, the high-end users, and the new users, and also for the biomedical research IT. And then I'm also the treasurer of HPC XXL. And as I really, one of the reasons I come to HPC XXL are those site update talks, because this is really a good way to get an overview of what other sites are doing, hook up with people, and talk about the solutions that they've implemented to make their HPC systems more useful for their users. So I want to do a quick overview of the high-performance computing environment that we have at IU, and then do an intro of two projects that we've been doing for a couple of years, and then a few tools that we've developed recently. Indiana is a state in the Midwest in the US. You may recognize Chicago. Indianapolis is about 3 hours south by car, and then Bloomington, the main campus, is about an hour south of Indianapolis. So the university has 8 campuses. 2 of them are the big research campuses, Indianapolis and Bloomington, and then 6 smaller campuses. The IT organization overall is distributed across the 8 campuses with 700 staff, full-time staff, and about 500 part-time staff. 180 of them are in research technologies, which is the division within UITS that is responsible for providing research IT services. So I'm going to go rather quickly through the compute environment. It hasn't changed much in the last couple of years. Our biggest system is a Cray XC6, XK7 system, very similar to what Blue Waters is at NCSA. It has a peak performance of a petaflop coming out of the K20 GPUs that we have in the system. And one of the things that is interesting about the way Indiana University does look at access to those systems, everybody can basically create an account on most of our research computing systems. So we're not doing allocation, not even on the Cray system, but if you are a staff member, faculty, or graduate student, you can just go to our central IT tool, request an account, and within a few hours you can be up and running on the Cray. If you're an undergraduate student, you have to find a faculty sponsor to get onto the system. But for our throughput Linux clusters, you can also, as an undergraduate, simply create an account and run things on the system. This has advantages and disadvantages when it comes to how effective and how efficient the systems are used, but it's super beneficial for making HPC accessible to fields of science that have traditionally not used high-performance computing. The newest acquisition that we have is a Cray XC30, XC40, 560 compute nodes, all of them dual CPU nodes, with the idea to make this available to larger jobs, as in jobs that can consume half the machine or more, 256 compute nodes or more, and also dedicated to an initiative that IU has done in the last couple of years, which is a Grand Challenge projects, which set aside a certain amount of money to fund specific research in a specific area. And they get some dedicated time on this machine. And then we have 2 Linux clusters, both with Intel processors and Ethernet interconnect. One of them is the oldest one is about 400 compute nodes now karst, 10 gig E interconnect, nothing really special about the system. And then a very similar system without a picture for support for high memory needs with up to 512 gigabyte of main memory. Storage systems, we are currently in the process of putting in one or 2 new storage systems, depending on how you look at it, to replace and augment our Lustre scratch space. We currently have 5 petabyte of Lustre scratch space with Lustre on LDiskFS. And the system that we're going to put in, Slate, will be 4 petabyte of persistent storage and 8 petabyte of condo storage that we sell to users. And this is with Lustre on CFS and CFS pools. And then we also, together with the Texas Advanced Compute Center, operate Wrangler, which is a NSF-funded project to provide support for storing data sets for the national audience. For convenience storage, we also operate a research file system, which is GPFS driven. And we're currently doing acceptance testing on the new GPFS version 4 with encryption in GPFS, not encrypted drives, but encryption in GPFS, and asynchronous replication between the Bloomington and the Indianapolis location. So the new system is 4 petabyte usable size, meaning we have 8 petabyte of disk, 4 of them in Bloomington and 4 of them about 75 kilometers away in Indianapolis, with asynchronous replication for disaster recovery. Very similar setup on our tape archive. Total capacity of the tape archive is 60 petabytes, of which there's about 30 usable, again with replication between our 2 big campuses, Bloomington and Indianapolis. It's based on HPSS, and we make it available through SFTP, HSI, and the HPSS API. Most of our storage systems are HIPAA aligned, so we support EPHI workflows for electronically protected health information, together with researchers that then take care of the encryption part of the data. With this, I'll turn to the more interesting part of the presentation, which is an overview of the 2 projects. First one is Jetstream with Dave. Where's Dave? Over there. Dave gave an overview about Jetstream last year. I'm going to just give an update and some statistics of the last year of operation. Jetstream is an NSF-funded resource put in place specifically to support researchers that are normally not well served by NSF-funded cyber infrastructure. So we're talking about users that can't make use of large-scale batch-driven supercomputers. The system is VM-based with OpenStack, and the idea is that users can sign up for long-running persistent virtual machines. So if users have a very specific software stack, or they have the need to run very long, or they have web gateways that they want to serve to their community, those are all projects that are supported on Jetstream. And it's, as I said, you can run MPI jobs on the system, but the system isn't really designed to run large-scale parallel workloads. The system is designed to support software stacks and applications that are normally not well supported in a batch-driven system. It's split into regions, one of them at the Texas Advanced Computing Center in Austin and the other one at IU in Bloomington. Both sites have exactly the same hardware setup, 320 compute nodes, an internal 40 gig interconnect, and then connected to Internet 2 and the National Research Backbone with 100 gigabit and the dedicated connection into the dedicated Exceed network. There's a small development instance in Arizona to support the development of the Atmosphere middleware. This is just an idea of the stack. So we run OpenStack and Ceph, then the Atmosphere middleware on top of it that provides an API and a web application. Web application includes the ability to do SSH in the browser, to do VNC from an X server that runs inside the VMs. So end users can get up and running just by being in the web browser and running and using the APIs that we have in the web. You can also, more advanced users can use the Atmosphere APIs or even the OpenStack APIs. One of the things that we wanted to achieve with Jetstream is really a large number of users, preferably from a different set of scientific domains and institutions. So far, we've 314 active Exceed research projects with over 2,000 users from over 200 different institutions. None of them really high-scaling parallel workloads, but all of them with a need to run either long-running jobs or have a different software stack. One of the more interesting use cases are gateways, which will then multiply the user base on the system quite a bit by running the user interface on Jetstream and then maybe running the jobs on Jetstream as well, or running the jobs on Stampede or on Comet. Thanks to the 2 regions that we operate, in the last year, we achieved 100% system availability by region. We've also a special agreement with MathWorks to provide MATLAB to all the users of Jetstream. So that's one of the use cases that, if you know how to do MATLAB on a HPC system, that's of course easily doable also in a command line environment. But a lot of users in MATLAB really want to explore the graphical features of MATLAB, and this is something that is well supported on Jetstream. And then we try to serve a lot of the science domains that normally have a hard time on supercomputers or don't have the need for a supercomputer to begin with. Second project is an IU internal one to help us reach out to non-traditional HPC users. That is run by Abhinav Tota, who gave the Singularity tutorial yesterday. It's basically the idea to provision GNOME desktops to end users, but not just for administration of jobs, but also for running actual compute workloads. We've gone with a product called Thinlink from Sentio, which is a Swedish company, and it implements a bunch of convenience wrappers around VNC over SSH. So it's on our cluster side, we provide SSH in the way we normally do, which includes two-factor authentication, and the VNC protocol gets tunneled through it. This is the desktop as it looks in our current incarnation, which is the research desktop. It's nothing special. It's based on Mate, which is a GNOME 2 fork, instead of going with GNOME 3, which is a little bit more resource intensive. We've customized it a bit to really help new users along, where for new users it's hard enough to get around the concept of doing remote computing, but then if they go to a supercomputer, you have to do this remotely and unattended in a batch environment. Here, we hope that we provide enough tools to ease people into this. So for example, I'll show this at the end, we have a graphical job manager which will basically just take the output of QStat and make that available in a graphical fashion. We provide a convenience export of Box, which is IU's solution for cloud storage. We have a web GUI for our scholarly data archive, and we have an icon that will do specifically interactive job. So you double click it, it automatically submits the job and gives you a terminal on a compute node. So traditionally, users can go to the login nodes on our clusters directly with SSH, or they can go through a load balancing gateway and then directly to one of the desktops running on our current 25 nodes. So right now we have two systems. We have an older version that works with specifically one of our supercomputers, and a new one that we will put in place that acts as a front end to all of our machines. And then you can still SSH to our login nodes, or you can actually submit jobs directly from the research desktop to one of our machines, where the nodes are also job submission nodes within our batch system. But you can also run things on the desktop itself. So we have a C groups-based script that will take care of the resource needs of individual users and make sure that the system doesn't get overwhelmed by multiple users. But we encourage users to use the batch system, but we have no issue with people running limited workloads on those nodes as well, for convenience. One of the things that users use the nodes for as well is data transfer. We have the same file systems mounted on all of our HPC machines, as most centers have. And then you can use those nodes that have a 10 gig e-interconnect into our core switch to also do data transfers to the tape archive, do data transfers between the file systems. Those are some of the applications that we've installed. Some of them are just HPC applications that come with a GUI, like a linear map, total view, Vampire, or COMSOL multiphysics. Instead of having to do client server in the batch environment, you can do it directly on those nodes. And then we have worked with various research groups on campus to provide a dedicated environment for users. We have a crystallography lab that has the need to run a lot of different crystallography applications. So they have created those on the system, and they can now use them in their research. Or we have a class in mathematics that teaches Fortran, and instead of the students having to install the GNU Fortran compiler on Windows with Cygwin, they can just use the research desktop to do Fortran compilation on those nodes. Another interesting use case is when we have researchers that invite other collaborators to be at IU for a research semester, a couple of months. As they go back to their home institution, they can continue to use the systems at the university in the same environment that they have when they were at the Bloomington campus. VNC over SSH is pretty usable even over 50, 100 millisecond latency. At the beginning of the year, we did a user survey across 900 active users on the system, and there's some standardized questions that you ask about how satisfied are you with the service. And on average, more than 80% said it's really important for us to not just have a graphical interface as a way to get to the supercomputers, but also as a way to get my work done with that infrastructure. And we've looked at the statistics, and we got more than 250 new users that have basically never run a batch job before through this environment. Right now it's our task to figure out, is the system big enough for them? Is this something that they can do all their research with, or is this something where we want to work with them to migrate them into the batch system? And now just a few screenshots on some of the tools that we've built. The first thing is Pathfinder. We have a knowledge base at IU, which we encourage students and people who have questions about IT to go to. And one of the things that if you put in, how do I get started with supercomputers at IU, is an article that says, how do I decide which of the computing environments that we make available is right for me? Goes a link. You can, first of all, contact a team and actually talk to a person, or you can take a little bit of an online survey. It consists of 10 questions. Model to figure out, do you need to run on a Cray with low latency interconnect? Can you do on Karst with not so much of a low latency interconnect, or do you have interactive needs? And it also has questions like, I need to run a Windows application, right? Which we currently don't support, but it's always important to at least have the question there to get an idea of what people want to do. You don't have to answer all of them. And if you hit the submit button at the end, you get at the top, you get all systems, and you get a percentage of what we believe is the right fit for you. For example, I selected Karst here, which is, according to the math, only a 70% match. And then for all the questions that do not match with what we think is the right answer for the system, you get a direct link, you get an explanation, and you also get links to our knowledge base that explain, you need this, but we only have this. Here's a way how to compensate, right? In this case, the question was, I basically want to run interactively, which you can on Karst if you use the interactive queue and if you know how to do batch jobs. And to get you started, those are the KB entries. Pick one of them to get started. So this is another tool. Not that we don't like answering those questions for users, but most new users are rather afraid to contact support with a very basic question like, you got 3 systems, which one is right for me? So this is a good way of having people go through the questionnaire themselves. And if you scroll down, you actually get a sign-up link. So you can immediately create an account, and you get another link that goes to our contact form. So if they have additional questions, they can immediately contact us or create the account. Then we're working on like most centers, we're working on a dashboard that shows some of the live statistics of our systems, and then also everything that's related to using our resources, creating an account, looking at how much resources you've consumed. One of the interesting things we put together is a wait time visualizer based on Moab Web Services. You can basically you can put down which machine you want to use, which queue, and for how long. And then you get a little rectangle drawn into the right space in a visualized way how much resource you're consuming and when that job will run, right? So you basically see from now up to 160 hours into the future what resources are available. And then I did the screenshot on I think Friday or so, and we had a system maintenance on Sunday. So you also see that the system maintenance is in there. So if you ask for anything that's longer than 40 hours, and yes, we have queues where you can ask for much more than 40 hours runtime, your job will never run until 60 hours from now. Right? This is the graphical tool that's based on Sanity, which is a command line utility that will render GTK plus dialogues in GNOME. So it's a very handy way of writing a shell script, but still using a graphical interface to either ask the user a question or present the user with data. So this is basically the outset of qstat-a, which everybody on the command line qstat-a and then grep for your username and everything. And this is how power users know what the system is, how full the system is. But with this, you can actually click on the table headings and you can sort it. You can look at just your jobs or everyone's jobs. This is what the interactive job icon does. It basically opens the terminal and it also gives you a dialog and it gives you the exact command that was used. So if a user really doesn't want to do it like this anymore, but wants to do it on the command line, this is immediately applicable. And then just as a teaser at the end, if you have done this, I would love to hear from you. Maybe not right after this talk, since I'm probably running late, but find me later this week. We started pushing our statistics that we get from our HPC compute and storage system into Tableau, which is an enterprise business intelligence tool that the university uses for decision making. And so we've created all kinds of weird charts to begin with, showing the resource utilization of our HPC compute and storage system over time, so that we are in the same pool as other other parts of the IT shop. So this is, for example, the number of storage projects that we have on our DC2 file system and the throughput. The graphs itself are not that interesting. Everybody can do this, but I'd be interested to hear from you if you have done this with Tableau.